Hello everyone, let's start with this lesson, Time Domain Analysis Module for Signal Linear System, Discrete System. Hello everyone, today we begin part 5. The third section is a classical solution to the difference equation. The main content of this section is as follows. Firstly, the iterative solution of difference equation is introduced. Secondly, the classical solution of difference equation is introduced. Finally, an example analysis is given. First, we introduce the iterative solution to the difference equation. The iterative method is the most basic method to solve the difference equation. It is solved by using the recursive relation of the equation itself, but it has the disadvantage of not getting the parse value of the output sequence y of k. Let's do a specific example. We know the difference equation y of k is equal to the 3 times y of k minus 1 plus epsilon of k. And we know our initial condition, y of minus 1 is equal to 0. Solving the difference equation, then we can follow the iterative relationship of the difference equation. Solve recursively. The specific solution method is as follows. Let's say k is equal to 0, 1, 2, 3, and so on. Then we can get the value of y of k at each sequence point. This method is simple and straightforward, but you can't get an analytic representation of y of k. So you can see that the initial output sequence of y of k is the following. This method is very simple and intuitive. That is the great thing about it. The second aspect is the classical solution to the difference equation. The time domain solutions of difference equations can be divided into homogeneous solution and special solutions. First, let's talk about homogeneous solutions to difference equations. The homogeneous solution of the difference equation is closely related to the form of the characteristic roots. We get the characteristic roots by solving the characteristic equation. The characteristic root determines the form of the homogeneous solution. After the form of homogeneous solution in difference equation is determined, how to determine its undetermined coefficient? It is usually determined by the boundary conditions. We can see that from the original equation, we set k equal to 0, get its initial conditions y of 0, and take y of 0 back to its homogeneous solution. We can find its undetermined coefficient c. So we get the form of the homogeneous solution. That's the general process for solving homogeneous solutions. So let's summarize the steps to find the homogeneous solution to a difference equation. The characteristic equation of the difference equation is determined by the difference equation. We can solve for the characteristic root, determined by the form of the characteristic root, the homogeneous solution of the difference equation. Finally, the undetermined coefficient of homogeneous solution is determined from the initial state. So let's do a couple of examples. According to the form of the characteristic root, 3 cases of the solution generally including the case of single, multiple, and conjugate complex roots. First, let's look at the case of the single root, given the initial conditions for the difference equation. So let's solve for that. and you can see the solution process. According to the second-order difference equation, let's determine the form of the characteristic equation. You get the characteristic root lambda 1, lambda 2 is a single root form. Thus, the expression of the homogeneous solution y of k is determined. So the undetermined coefficient C1, C2 is determined by who? We can determine by the initial conditions. According to our initial conditions, the value of y of 0, y of 1. Let's take that into the equation. You can see two equations and two unknowns, so we can figure out what is C1 and C2. After C1 and C2 are determined, let's bring it back to this expression for its homogeneous solution. So you can see that the solution to the final homogeneous solution y of k is for obvious form. This is a single root case. The general form of homogeneous solution to a single root is this form of the exponential form. Now let's do another example of double root. Suppose the difference equation is the following. Find its homogeneous solution. This is a third-order difference equation, so the characteristic equation is expressed as follows. Its characteristic root is a triple root form, so the solution to the decision is an expression that looks like this. As for C1, C2, C3 in the analytic form, we can solve it based on the boundary conditions. What is the form of the second aspect particular solution? In general, linear time invariant LTI systems have the same form of input and output. The form of the particular solution depends on the form of the input excitation. Between the most common input excitation and the output particular solution, the form comparison table is as follows. In this table, what we want you to be familiar with are the four forms in red marking. If you want to, I want you to compare the input with the output. In our course study, the frequency of these four forms is relatively high. Let's do a specific example. We know that the difference equation gives the initial conditions y of -1 is equal to 1 requires a complete solution. So first, let's find the homogeneous solution. The characteristic equation is obtained from the difference equation. So the characteristic root lambda is equal to -2. I get the homogeneous solution in the form C1 times -2 to the k. So let's look at a particular solution. According to the excitation is 5 times the epsilon of k. So its particular solution is a constant. Let's say that yp of k is equal to c. How do we determine the undetermined constant c? We need to bring it to the original difference equation to determine the exact value of the particular solution. You can see that c is equal to 5/3. After determining the form of the particular solution, the full response is determined by the sum of the homogeneous solution and the particular solution. So C1 on this side, we need to use the initial conditions to determine accordingly. So we get the form of the total solution. So y of -1 is equal to 1 based on the boundary condition. We can iterate over the initial value at k equals 0, and that brings us to the analytic expression for the total solution. So we know that C1 is equal to 4/3. Therefore, the total solution y of k can be figured out. This is a classical solution to a difference equation, and you have to be careful when you are solving it. After we get the form of the full solution, the undetermined coefficients are determined by the initial conditions. Thanks. That's all for today. Thank you.